Right, so yeah, as I mentioned, ignore this title. I meant to say Bresenham's algorithm. So we're going to carry on from page 56, I believe, in the notes. Okay, so on Monday we introduced the idea of rasterization. So this is essentially you have a screen on a computer screen or your phones. And the way that the screens work is they have lots and lots of little squares called pixels. We color or illuminate those pixels, each pixel in a particular color. And as you're viewing the screen, your brain sort of interprets the pixel array as an image. Okay, the proper word for a pixel array is a raster array. Okay, so raster and rasterization is what we're looking at. So the raster array is the pixels displayed on screen. Rasterization is the process of approximating the idealized image. That's what we want to show. That's like the perfect image. We can never have that because pixels are only ever an approximation. The fundamental problem in rasterization starts with drawing straight lines. Okay. Everything else follows after that. So curves, what have you, follow after. But straight lines is the fundamental problem. So we're going to look at line drawing algorithms. And how all these algorithms work, well, we're only looking at 3 of them, is we have a driving axis. So that's either the horizontal or the vertical axis. And essentially, with the driving axis, you just step along from one pixel to the next. So if X is your driving axis, you just step along each pixel, starting on the left and going left to right. If Y is your driving axis, start at the bottom and you go up. And you have to calculate the other coordinate. So you know what your, if X is your driving axis, you know what your next X coordinate would be because you just add 1 to it. But your Y coordinate will depend upon the slope of your line. On Monday, we looked at 2 algorithms. We looked at the DSC algorithm, which is essentially Cartesian equation of a straight line, y equals mx plus c. But that's slow. It's slow because we have to calculate lots of what we call floating point operations. Floating point operations are operations on real numbers. Now, computers, they work in binary. Okay, so binary methods are fastest. But failing that, integer methods are faster. If a computer has to work using real numbers, i.e. decimal numbers, it's slower for the computer. Now, to you and I, the difference for a single application is tiny. You're talking microseconds. But these methods are being called millions of times a second. So if you can say fractions of a second at this level, is much better. Okay, so we looked at DSC algorithm. The DDA algorithm simply adds a gradient at each step. Okay, so that's just a recap of what we did on Monday. Okay, what we're going to be looking at today is the method everyone uses. Okay, no one uses DSC, no one uses DDA because they're too slow. Okay, the Bresenham algorithm, late 60s, it was invented and no one's improved on it since. So might as well use it. And what's so good about it is it only uses integers. It never needs to use any decimal numbers, only ever uses whole numbers. And it's quite a clever little bit of math, really. Why is it better? Well, as I mentioned, integer arithmetic is much more computationally efficient than floating point arithmetic. And how it works is instead of calculating the, so for example, if we have X as our driving axis, so we're stepping along in the X direction, instead of calculating Y using, for example, the equation of a line, what we do is we calculate an error. Now that error is between our idealized line and pixels which straddle the line. And we just pick the pixel with the smallest error. Okay, and depending on which pixel we choose, so at each step along the driving axis, we have a choice between 2 pixels. depending on which pixel we choose, we update the error. Okay, so if I show you via the diagram on the top of page 56, okay, what we have here is this is a very, very simple 6 pixel raster array. Let's assume that this pixel here has been illuminated. Okay, it sort of makes sense. This is our idealized line, big black line. Okay, so the pixel are xi, yi, that's been drawn. So if we step along in the driving axis, 1 pixel to the right, so we're now at xi plus 1, you can see that the idealized line straddles the center of 2 pixels. So we have this pixel, which I've called the east pixel, okay, and this pixel, which I've called the northeast pixel. So E for east, NE for northeast. Okay, so what we do is we calculate the distance between the pixel centers and the idealized line. Okay, so DNE is that distance there, DE is that longer distance there. So by visual inspection, you can clearly see that this is a pixel we should be illuminating because DNE is less than DE. Okay, so that's how we make the choice. So at the bottom there, the yi plus 1 means what's the pixel. Okay, yi is our current pixel. Yi plus 1, that's the next pixel we're going to illuminate. Okay, so if xi, yi has been illuminated, okay, we know what xi plus 1 is because that's just add 1 to xi, but we don't know what y subscript I plus 1 is. And we use this type of thing. But we can improve on this because the distance, okay, remember, pixels are just 1 unit wide. So the distance between these centers is going to be 1. So therefore, these DNE and DE, they're going to be some fraction less than 1. And I mentioned we don't want that. We want integers. So we do something quite cunning here. Okay, so if I let x prime and y prime be the actual coordinates of the idealized line, okay, the distance from the east pixel, so this distance here is the actual coordinate at that point minus the center of that pixel there. Okay, so that pixel has a y coordinate of yi. That point there has a y coordinate of y prime. So that gives us DE. DNE, okay, it has a y coordinate of yi plus 1. And obviously, we've still got the y prime. And what we do is we create an error. Okay, this epsilon means error. And I say, okay, I'm going to let the error be DE minus DNE. So the distance, the east pixel, between the east pixel center and our line, and the distance between the northeast pixel center and our line. Okay, so if I substitute these into this, I get this expression. So y dash or y prime is our actual line, yi is this y coordinate here. Okay, so it's that y coordinate. And what this means is when our error is negative, this distance DE will be less than DNE. So when that distance is negative, okay, so when this is negative, DE must be less than DNE. So we calculate, or we assume that our pixel to the east is chosen. So we'll have this pixel. If it's positive, that means DE must be greater than DNE. And we go up to that pixel. So what we're going to do is calculate the error. If it's positive, we go up. If it's negative, we just go across. So positive, we go across and up. So to the northeast. If it's negative, we just go to the east. Okay, but calculating the error at each step, again, it's more unnecessary calculation. What we try and do is just add an increment of our error. And what it turns out as being is whether we go to the east pixel or the northeast pixel, the error is always constant because the slope of a straight line is always constant wherever you are on the line. Okay, actually, I'll just show you a derivation of that. So I've got a expression on the board. Okay, I'll just show you where this comes from. So, I mean, this is sort of given in the notes as well, but it's always easier when you're following somebody's logic and what line of working. So what I'm going to do is I'm going to start with the equation of a straight line. And as you know, that's y equals mx. So m is the change in y divided by the change in x plus c. That's our equation of a straight line. So delta y over delta x is our gradient, c is our y-intercept. Remember, we know what delta y and delta x are. That's just the distance in the x and y directions between our start point of our line and our end point. And we're going to let our error, epsilon, be 2y minus 2yi minus 1. Oh, sorry about that. I'm going to turn autofocus off. Okay, so that error, that comes from dE minus dNE. I should really say y prime, shouldn't I, there? Okay, well, all we do is, well, y prime is our exact line, which is given by this. Okay, I should really put primes on the x's. Okay, so what I'm going to do is substitute this in place of there. But what I'm going to do is I want the error at the next pixel along. So let's say I've got 4 pixels. That's xi. That's xi plus 1. That's yi plus 1. And let's say I've got the line. Okay. I need the error for my next pixels along. So what I'm going to do is, instead of saying x dash, if this one's already been illuminated, my x dash is going to be xi plus 1. So what I've got to do is say, okay, that's going to be 2 mx, but x, I want it at the next pixel along. I want to know what the error is at this pixel, because I've already shaded this one. What is the error at this pixel? So hence, instead of x dash, I have x plus 1, or xi plus 1. Okay, that's plus c minus 2yi minus 1. And all I'm going to do is rearrange that. Okay, I want to rearrange it so I've got a nice expression. So if I multiply everything by delta x, just to get rid of the fraction, so what I've got epsilon delta x is equal to 2xi delta y. So that's that one. 2 delta y. And I've got 2c delta x, because if I'm multiplying everything by delta x, I've got 2c delta x minus 2yi delta x minus delta x. So all I've done there is multiplied throughout by delta x, and I've done some expanding brackets as well. Right, so now my error has been multiplied by delta x. But remember, we're only interested in what the sign of the error is. We're not interested in its value. We're only checking whether it's greater than less than 1. So that means what I can then do is I can just say, well, why don't I just let my error be error times delta x? I'm not interested in the value. I'm just interested in the sign. So letting error be error times delta x does not change whether it's going to be positive or negative. So if that's the case, what I end up with is, given a set of coordinates, I'm going to end up with a function for my error. Okay, and that's essentially just what we've got written down here. So I'm just writing down exactly the same. Okay, so that's my error function. xi is known because that's the coordinate I've just shaded. Delta y and delta x are constant because they're calculated from the start and end point of a line. C, well, that's actually going to disappear in a minute, but that's the point at where the straight line crosses the y-axis. So I know all of the stuff on the right-hand side. I could use that to calculate the error for every pixel along. That's inefficient. What I'm going to do is see, okay, what's the change in this error as I step each pixel along? And then all I have to do is add the change in error rather than recalculating all of that. So the change in error, so the change in E is dependent, epsilon, not E. The change in the epsilon is dependent upon whether I chose to render the pixel to the east or whether I went up one and went to the northeast. Okay, so the change in error, what's the change in error from this? Oops, sorry. What's the change in error from? So I know the error at this point. As I go to xi plus 1, how's my error going to change across this distance? So that's going to be the error at the next point along. Okay, so this is the x coordinate at the next pixel, the pixel to the right. The y coordinate, I don't know. Okay, this I plus 1 is quite important. That should be a subscript. Okay, so that's a coordinate of the pixel I don't know. That's going to be the error at the pixel on the right minus the error at the current pixel. And all I do is use this expression here, this function, subtract it for when xi equals xi plus 1 and yi equals yi plus 1 in subscript. And subtract from that function. Okay, so a bit of algebra. So instead of xi, I've got xi plus 1. 2 delta y is the same, plus 2c delta x is the same. Okay, instead of yi, I've got yi plus 1. Plus 1 delta x minus delta x. So all that is this function with xi plus 1 and y subscript I plus 1. I don't know what that is. Okay, this could be either it could be y I or it could be yi plus 1. It's one of two states. And from that I subtract this thing again, but with just xi, yi, so just this line. So all I'm going to do is write that line but subtracted. So I've got minus 2xi delta y minus 2 delta y minus 2c delta x plus 2yi delta x plus delta x. So I'm subtracting this from this. Okay, so I've got quite a bit to cancel out here. If I expand this bracket out, I get 2xi delta y, but then I'm subtracting 2xi delta y. So that's going to cancel out. Okay, so that xi there cancels out. But then I'm left with 2 delta y. Okay, plus 2 delta y minus 2 delta y cancels out. Plus 2c delta x minus 2c delta x cancels out. Then I've got 2 or minus 2 yi plus 1 delta x plus 2 y delta x. Okay, so I can't cancel those two out because this and this aren't the same. But the minus x plus x cancels out. So what this means is that's my expression for change in error. So rather than having to calculate that big horrible function up here, I've got a nice function here. But it's dependent upon yi plus 1. I don't know what that is. It could be that I went to this pixel. In that case, yi plus 1 would just be yi I. But if I went to the pixel above, the yi plus 1 would be yi added to 1. So I've got two different states. I've got two different things that the change in error could be. So if yi plus 1 was equal to yi, that means I chose the pixel to the east. Okay, we got the change in error if I went to the east pixel, so I'd use a subscript e. Okay, would be 2 delta y minus 2 yi delta x plus 2 yi delta x. So here, the yi plus 1 is simply yi. And that comes down to 2 delta y. Okay, so I'm putting a little underline on there. That's finished. That's if we went to the east pixel. What if we went to the northeast pixel? So else if yi plus 1 is equal to yi plus 1, okay, in other words, I'm adding 1, so I'm going up 1. Okay, the change in the error if I went to the northeast pixel would be this, but instead of yi plus 1, I substitute that in. It's 2 delta y minus 2 yi plus 1 delta x plus 2 yi delta x. Okay. Let's expand out the bracket. So I've got minus 2 yi delta x minus 2 delta x plus 2 yi delta x. Okay, as you can see, this term cancels out with that term. I'm left with 2 delta y minus 2 delta x. Okay, after all of that, lots of algebra, rather tedious algebra, our change in the error comes down, if we went to the east, we just add whatever 2 delta y is. Now, delta y is the distance between the start point and the end point in the y direction. If, however, we went to the northeast pixel, we add 2 delta y minus 2 delta x. Very, very simple calculations. We don't have to bother with that difficult, well, that nasty error calculation. But what is my starting error? Okay, we need some point to start from. Okay, and to do that, all we do is substitute the equation of a straight line into our error value. So I'm just going to move this up a bit. So remember, we had y equals mx, so the gradient times x plus c. So if we rearrange that, it's quite simply to make c the subject. Okay, we have c equals y minus mx. Okay, what we're going to do now is substitute that into the expression for the error. So remember, it was just going to write it down, the error again, just so you can see it. Minus 2i delta x. Okay, so that was my error. Have you got all this down? It's kind of repeated from the notes. Okay, so all I'm going to do for the starting error, so this is for the first error. Okay, I'm going to substitute in this expression in place of c. Okay, so I'm going to call the first error epsilon 0. So that's your initial error. So we have 2xi delta y plus 2 delta y plus 2, and this is where the c comes in. But yi minus delta y over delta x xi. Okay, so that's multiplied by delta x minus 2yi delta x minus delta x. Okay, all I have to do now is simplify this. Okay, and it actually simplifies quite significantly. So I've got 2xi delta y, and I've got where have we got here? So 2xi delta y minus 2xi delta y, because you've got delta x on the bottom times delta x. So that will cross out with that term. I've got 2 delta y, doesn't cross out with anything. Then I've got 2yi delta x, but then I've got minus 2yi delta x. So that will cross out with that. I'm just left with delta x. That's it. Okay, so lots and lots of algebra, but at the end of it, we have 3 expressions. This is our first error. Notice it's just in terms of delta y and delta x. Very, very simple. So that's our first error. We have, oops, sorry, I'm just trying to, okay, we have the error, the change in error if we chose the pixel to the east to illuminate, or we've got the change in error if we chose the pixel to the northeast. All of those expressions only use delta y and delta x. By definition, delta y and delta x must be integers, because they're just the distance between 2 pixels, and pixels are all integers. So what does this mean for our algorithm? Okay, so I'm just going to switch back to the slides now. Okay, so for our algorithm, and that's just what I sort of derived there. And that, again, that's the derivation of what we just did on the visualizer. We got this. Okay, so let's say we have 2 endpoints, A and B, and we have a raster array. Like with the DDA algorithm, we round A and B to the nearest integers, so they fall exactly on a pixel. And we start with x and y being the start pixel A. We calculate what's the change in x and the change in y, and then we calculate our errors. Okay, so our error is 2 delta y minus delta x, which we just derived. The change in error, if we went to the east pixel, was 2 delta y, and the change in error if we went to the northeast pixel was 2 delta y minus delta x. Okay, so that's all pre-calculated, and these are all integers. So we loop across the driving axis, you rasterize the current pixel. If the error is negative, you add delta epsilon e to it. Else, if the error was positive, you add delta epsilon northeast to it, and you add 1 to y, because you've chosen the next pixel up. And you just add 1 to your x coordinate. So it turns out, once you've done all these initialization routines, it's a very, very simple algorithm. If you want it as a flow diagram, there you go. Quite similar to DDA, except for we've got this choice down here about what the error is. So if the error is negative, you just add, you go to the east pixel, and then you add 1 to x. If the error is positive, you add 1 to y because you've gone to the northeast pixel, and then add 1 to x. Okay, that's your output. So all I've done here is I've changed my line drawing program to use the Bresenham algorithm rather than DDA, and you can see it's identical. Okay, but it's a hell of a lot faster than doing it using DDA. Okay, so what with the remaining 10 minutes or so we got left,